All right, physical science, I'm going to go through and do some examples of how to draw Lewis structures. So I've come up with some examples that are similar to what's on this week's assignment, and I'll talk about how we're going to try it. But basically, you're going to write down a chemical formula, add up some electrons, and then try and draw the structure. So we'll start off simple and we'll just do single atoms. So if I said draw the Lewis structure for sulfur, right? Sulfur is element, right? Element symbol S. So you look it up, and sulfur, okay, for these single atom ones, you look up their atomic number. So, oops, this is got 16 protons. And so it also has 16 electrons. It's neutral. So if we were to draw a Bohr model, you'd put, this is overkill. 1, 2 electrons on the inner ring. 1, 2, 3, 4, 5, 6, 7, 8. So I'm up to 10, 11, 12, 13, 14, 15, 16. Okay, but we, for the Lewis structure, right, you just want to draw the valence electrons, the outermost electrons. So what I do, I look at that third ring and I just go, it's in group 6. 1, 2, 3, 4, 5, 6. Okay, so you can tell sulfur is short of a full octet by 2 electrons, which, you know, ultimately it's going to either share electrons, right? 2 electrons with something else to get to 8, or it's going to have to steal electrons from a metal, and it would steal 2 of them. So the Lewis structure ends up being pretty useful for predicting what kind of bonds or how it will bond to things. Okay, so let's just keep going. Potassium is a metal. So it's going to have a lot less valence electrons. So I look, okay, on my periodic table, potassium is in that first column. It's known as group 1A, so I just put a single dot, right? That doesn't mean it only has 1 electron. It just has 1 in its outermost shell, right? Potassium really has 19 electrons. It has more electrons than sulfur, but in its valence shell, it has just 1. So we draw it that way. Okay, aluminum, and then we'll make a compound. Okay, aluminum is also, right, a metal. And you look, this one is in group 3, right? It's over right next to like silicon, that third column. So 1, 2, 3. And you're wondering, why am I putting them around 4 corners? Well, one, we deal with like these symbols on a flat piece of paper, so we kind of spread them out evenly around the outside. And it actually has to do with certain orbitals that electrons fall into. It turns out for each energy level, typical energy level, especially the second and third energy level, there's like these kind of 4 distinct orbitals that they go into, and they fill them in certain orders. Now, for drawing the dots, it really doesn't matter where you put them, as long as you kind of spread them out around the outside. Okay, so there's aluminum, and then we better do chlorine, because we're going to make aluminum chlorine, so, or chloride. So let's do chlorine. That's in group 7. 1, 2, 3, 4, 5, 6, 7. Okay, now, last week we talked about ionic compounds. When you have a metal plus a nonmetal, and they combine, the metal likes to give its electrons away. Well, aluminum would give one of its electrons to this chlorine, and now it's full, right? Let's do this one to a second chlorine. Now that one's full. 1, 2, 3, 4, 5, 6, 7. And then it gives the third electron to this chlorine. Now that one's full. So these are now called chloride. And it takes 3 chloride. Okay, -1, -1, -1. If these are all gone, that's called aluminum ion. And so you end up getting aluminum chloride, or AlCl3. Okay, that is, it's kind of hard to show. Ionic compounds, Lewis structures aren't really necessarily the best way to draw these. Actually, the better way would just be to write their chemical formula. And it's kind of tricky because electrons are moving from one atom to the other to form these ions. So you can't basically you can't show electrons being shared, which is what we're going to move into this week. So when we talk about covalent compounds or covalent molecules, okay, we're not going to move electrons from place to place. They're going to be stuck between two atoms and form covalent bonds. Okay, so let's do one of those. Let's do Br2, bromine. And the way we do this, you can either draw separate, you can draw the separate atoms, and then I'm going to show you a trick to just add things up. But I'll start with just drawing it. 1, 2, 3, 4, 5, 6, 7. And since I have a 2 there, that just means I have 2 bromines. 1, 2, 3, 4, 6, 7. And maybe you can see that both of them are 1 short of a full octet. So what happens is, right, the bromine shares one of its electron with the other bromine, right? Both of them share 1 electron. So this is called a pair of electrons. And it's the bonding pair. And you can redraw your Lewis structure. And every time you have a bonding pair, you put a little line. So that line basically represents those 2 electrons that I have in the circle. And this is the structure of bromine. Okay, and maybe if we were in class, you'd build this with a little molecular modeling kit, and it would just be 2 atoms hooked together with a little stick, and that stick represents a shared pair of electrons. So this Lewis structure with the dots, that's kind of the convention we use, but we can model them with like a ball and stick, or there's different ways that chemists do this to show 3D representations of these structures. So that's bromine. Okay, let's keep going on. Let's try hydrobromic acid. All right, hydrobromic acid. Well, we know bromine has 7 valence electrons. So here's the other way to do it. Instead of drawing each separately, you can just draw, let's see, 7. And hydrogen is in group 1. So you can take their valence electrons and add them together. So I know I have a total of 8 electrons to work with. Okay, and we're going to then just basically draw our structure. So I'm going to put H and Br next to each other. And we know that these are covalent compounds because hydrogen is a nonmetal and bromine is a nonmetal. Okay, so 2 nonmetals, you know that they have to be held together with shared electrons. So I put a line in between. And then you start adding up electrons. So each line represents 2 electrons. So there's 2. And I have 6 more to go to get to 8 valence electrons. So I'm going to throw them around here. And if you add up everything that's around bromine, you have a total of 8, right? 6 dots and a line. That makes 8. And then hydrogen is the one exception to the octet rule, because when we're doing Lewis structures, because it only needs 2 electrons to be happy. Because it's such a small atom, remember that inner orbital only contains 2 electrons. So hydrogen is happy with just that bond because that bond has 2 electrons. So that's hydrobromic acid. Okay, and let's try another. Carbon dioxide, this one, maybe you saw on the slideshow as you're going through the notes with Mr. England or myself. So let's do this. Carbon is in group 4. So again, you count columns. 1, 2, 3, 4. Oxygen is in group 6. And I have 2 oxygens. So I add these up. 4 plus 6 plus 6 is 16. Okay. So I have 16 dots or 16 electrons to deal with. The next step in a Lewis structure is to draw kind of a symmetric structure. So you usually have an atom that's kind of in the middle. So if I have 1 carbon and 2 oxygens, nature prefers symmetry. And so unless specified, you should try and draw it as symmetric as possible. Okay, so the way we do this, I have to put 16 dots around here to basically satisfy all the octets. Now, I like to do it this way. Connect them with single bonds, single lines. Okay, then fill up dots around the other sides of all the elements. And you're like, oh, that looks pretty good. Everything looks kind of full. I've got, dots around all the sides. I've got bonds in between. But if you add them up, I'm just going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And you're like, oh no, I've used too many electrons. So if you have too many electrons, and we only had 16 to work with, you have to reduce the total amount by sharing more. So this is kind of cool. You can satisfy the octet rule by erasing two pairs, a pair off an oxygen and a pair off a carbon, and replacing it with another bond. So it's like basically I'm taking away 4 electrons, but I only added back 2. And that still keeps 8 things around the oxygen and 8 things around the carbon. So that brought me down to 18 if you count them up. And I can do the same thing on the right hand side. And I end up with 8 electrons around both oxygens and 8 electrons around the carbon. You're thinking, well, how is that 8 around the carbon? Remember, that's 2, 4, 6, 8. So there are 8 electrons nearby the carbon to make it happy. And then there are 2, 4, 6, 8 electrons around the oxygen to make them happy. Okay, so that's what we're going for. That's carbon dioxide, okay, with double bonds. And double bonds meaning that there's 2 lines or 2 sets of electrons. Each line represents 2. Okay, let's try carbon tetrachloride, right? The prefix for 4 is tetra. Carbon tetrachloride. We use this in the semiconductor industry. Actually, let's make this more interesting. Let's do silicon tetrachloride. So we use this to grow silicon layers on wafers when we're about to produce processors for your phones or for your computer or anything like that. So very common chemical in the semiconductor industry. So silicon tetrachloride. Okay, you add up electrons. That's 4 because it's in group 4. Chlorine is in group 7. We did that one earlier. And I have 4 of them. Or you could also do this. Right? So that's 28 plus 4. I got a lot of electrons to deal with. So I set this up as symmetrically as possible. Conveniently, right? There's 4 chlorines. And I have to get 32 electrons. So here we go. Start with single bonds. 2, 4, 6, 8. Each line counts as 2. And then you gotta... So silicon right now has 8 around it. It's satisfied. But I need another 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 plus those 8 in the middle makes 32. And everything is satisfied, and it only uses single bonds in this one. So that's carbon tetrachloride, okay? Let's do ammonia. Actually, I wanted to pick one a little different. Sorry, let's try, how about PCl3. Okay, phosphorus trichloride. Phosphorus trichloride. Phosphorus is in group 5. Chlorine is in group 7. So that's 5 plus 21, 26. P, Cl, Cl, Cl. All right, 3 of them. I got 26 electrons to go. Let's just see. I'll do this with single bonds again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I go, well, what do? I don't know where to put my last 2. And you're like, well, phosphorus only has 3 bonds on it right now, so it has 6 electrons. I need to squeeze the last 2 electrons in on that phosphorus. And so that phosphorus gets what's called a lone pair, right? All those sets of dots, those are called lone pairs, and phosphorus has 1 lone pair, and right, those chlorines each have 3. So there you go. All right, we're almost done. I'll do a couple more. Let's look at acetylene. Acetylene is dicarbon dihydride. This is what we use in cutting torches and some other welding, right? Or metals work. So we burn it. Or maybe you remember Mr. England and I messing with the carbide cannon, shooting that little cannon that for demonstrating Newton's laws. We used acetylene gas to ignite that. So C2H2, carbon is in group 4. Hydrogen's the little one. It's in group 1, and I have 2 of them. Oops. Group 1, and I have 2 of them. So that's 8 plus 2 for a total of 10 electrons, 10 valence electrons. Okay, I can help out with acetylene. I know the carbons are in the middle, and the hydrogens are on the outside. Here we go. 2, 4, 6, 8, 10, 12, 14. To make everything satisfied with single bonds, I used up too many electrons. So the way we deal with that, erase 2 pairs, put in a bond. I can add them up. That's 2, 4, 6, 8, 10, 12. Too many. So I'm going to get rid of those pairs and introduce a triple bond. Okay, so acetylene holds a lot of energy because that bond, those electrons holding the carbon atoms together, store a lot of chemical potential. So acetylene has a triple bond. Okay, and then I'll do one more since we talked about them a little bit last week, and my video is starting to get long, so I need to shut it down here. But let's just look at nitrate. You guys remember maybe nitrate is one of those polyatomic ions. It's made up of 1 nitrogen and 3 oxygens. Okay, and it has a charge of -1. Okay, well, we didn't really talk about what a polyatomic ion was more than it's just multiple atoms, but really what it is, it's a cluster of atoms that are covalently bonded together, right? Held together with electrons, and with the charge, they can then bond to other ions. So here you go. Nitrogen with 3 oxygens, and then we got to deal with this. So nitrogen is a group 5 element. Oxygen is a group, here I'll do this, is a group 6 element, and there's 3 of them. And then this guy, you guys remember, negative charge means that there's 1 extra electron, usually stolen from some metal or some electron source. And so it's basically increasing our count of electrons by 1. If it was -2, it would increase it by 2. If it was, maybe we do one more example after this, but let's do this one. So this is 5 plus 18 plus 1, that's 24. So I put N in the middle, O's on the outside, and 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And you're like, oh, I'm done. But nitrogen has not met the octet rule yet. So I need to throw 2 on there, which is 26, which is too many. So in this case, this is kind of a weird one. I have 1 double bond in my nitrate, and that brings my count down to 24. So it turns out nitrate has a double bond and 2 single bonds. Okay, and it has some interesting properties. But we also throw on the fact that to get there, to satisfy all the octets, it needed 1 extra electron. So I show the charge in that upper right hand corner. Okay. And without that extra electron, you'd be at 23. And 23 is kind of a weird number. Typically chemical compounds, molecular compounds, like to form valence orbitals with even numbers of electrons. All right, the one kind of, if I can do it quickly, NH4 was the oddball, right? The oddball polyatomic ion. This one has a nitrogen and 4 hydrogens, and this is short 1 electron. It lost it, gave it away, so I'm going to subtract 1. So 5 plus 4 minus 1 is 8. So this is kind of a cool ion. You can already maybe see it. 2, 4, 6, 8. That's it. It's just nitrogen surrounded by hydrogen, and it has a positive charge. So there's your Lewis structures. Okay, for the assignment, you're given about, I don't know, a dozen Lewis structures to draw. You're just going to do them on a sheet of notebook paper, and then basically we're going to take a picture and attach it in Canvas or turn it in via Canvas. So you can't do Lewis structures with a keyboard and a mouse very easily. So do them on paper, try your best, and we'll work through more examples in class, and then you guys will submit them on Canvas. So have a good week.